benefits of science will be even more spectacular than we can ever imagine. I wanted to do something that is of long-range benefit to humankind. Practically everything we touch in our daily lives has been developed and improved through basic research. Science is taking us on an ever-accelerating journey into the future.
Please join me in welcoming to the stage 2026 ACS President Rigoberto Hernandez.
Wow, that video gets me every time. It's so inspiring. Let's give a round of applause to Fred Kavli and the Kavli Foundation for all that they do to accelerate science. Good evening and welcome. I am Rigoberto Hernandez, President of the American Chemical Society, and it is my sincere pleasure to welcome you to the Fall 2026 Fred Kavli Innovations in Chemistry Lecture, sponsored by the Kavli Foundation. Since its inception 14 years ago, the Fred Kavli Innovations in Chemistry Lecture has recognized the world's leading researchers and their transformative discoveries. Through these lectures, scientists bring new insights to major global challenges, including those related to sustainability and climate change, human health, food security, and water and energy needs. ACS is grateful to the Kavli Foundation for enabling us to showcase the achievements by outstanding researchers in the chemical sciences, addressing the challenges that matter to all of us. This lecture is especially meaningful as it takes place during ACS's sesquicentennial anniversary year. As we celebrate a century and a half of advancing chemistry and supporting the people who make scientific progress possible, we also look ahead to the discoveries and innovations that will shape the next 150 years. The Fred Kavli Innovations in Chemistry lecture embodies that spirit by highlighting researchers whose work is transforming our world. John Warner's pioneering work in green chemistry reflects that spirit of innovation and demonstrates how chemistry can help build a more sustainable future. Dr. Warner is a chemist, inventor, and entrepreneur widely recognized as a co-founder of the field of green chemistry. He co-authored the seminal 1998 book, Green Chemistry, Theory and Practice, with Paul Anastas, who's also in the room, establishing the principles that guide the design of safer chemicals and processes. I joined the Green Chemistry and Chemical Engineering conferences earlier this year in San Antonio. Nearly 30 years after his seminal book, the field continues to thrive because of Dr. Warner's unflinching scientific leadership and his genuine love for the community. Throughout his career, Dr. Warner has worked across academia and industry, holding more than 350 patents and publishing extensively in synthetic chemistry, material science, and polymer photochemistry. He is also a prolific entrepreneur, having founded and led multiple technology companies focused on translating sustainable chemistry into real-world applications. His work emphasizes invention-driven approaches to sustainability, demonstrating how new technologies can align environmental responsibility with commercial success. As co-founder of Beyond Benign and Technology Greenhouse, he continues to build platforms that accelerate the development and deployment of safer, more sustainable chemical innovations. This evening, Dr. Warner will present his lecture, Green Chemistry, The Missing Elements. His presentation asks what it would take for the chemical enterprise to deliver products that are simultaneously high-performing, cost-competitive, and inherently safer for human health and the environment. He will discuss how green chemistry reframes sustainability by focusing on the elimination of hazard at the design stage, embedding considerations such as molecular toxicity, persistence, bioaccumulation, and life cycle impact directly into research development and scale-up decisions. He will also highlight examples of how safer chemistries can meet or exceed performance targets while maintaining cost and manufacturability. Please join me in welcoming Dr. John Warner.
Well, thank you all. Thank you for that amazing introduction. I think all I can do now is disappoint you. It's a pleasure to be here and an honor. I can't thank enough the American Chemical Society and the leadership and the organizations that asked me to be here. Here goes. So, of course, we need to honor Fred Kavli and the Kavli Foundation. What an inspirational video and sincere honor to be associated with this individual. I want to start quickly by giving a disclaimer. And this is important to me. I don't claim to have any gifted insight. I don't claim to have any answers to the world's problems. If I ever come off sounding presumptuous, telling people you should think this or you should think this, please understand that is not where I'm coming from. I've been doing this for over 40 years, and I've come to see the world in a way. And with a bit of vulnerability, I'm going to share it with you. But please don't think that I have all the answers or even think I do. I look forward to having conversations and reframing these thoughts as the future goes forward. We're chemists. We're here in Chicago, the American Chemical Society, 13,500 chemists gathered. But if we leave this little bubble and go to society at large, they're afraid of us. Chemistry is that scary monster that's lurking underneath the bed that's going to come out and bite us. Open up the newspaper, turn on the radio, look on the internet. All we hear about is this is bad, this is scary, this is bad, this is scary. If the public is talking about chemistry, usually not very good. All right? It's like we're playing whack-a-mole. All right? Now, we chemists, we know a thing or two about moles. And if you wander the halls here, you may even encounter this thing, okay? We hear about something like endocrine disruptors, and it's like, whack. We hear something about climate change, and whack. We hear something like persistence and bioaccumulation, whack. We hear things about carcinogens, whack. We hear things about components that cause birth defects, whack, and they keep coming at us and at us and at us, and we try to wrap our heads around. We're asking ourselves, is this hype? Is this serious? And we don't really know. We, the only people in the world who understand molecular structure and its relationship to human health and the environment, aren't sure. This isn't a game. This is serious. And if we're confused, what does the general public think? All right, and so are we asking the right questions? You know, we ask, is this toxic? Should we ban this? Should we form regulations? But maybe a more important question is, why are we doing this? All right, so imagine those things. Imagine I'm making a red dye. Or someone is making a red dye. Okay, we know particle in the box, electron donating, electron withdrawing. We know how to get a red chromophore, all right? We know how to make that red chromophore stick to a fabric. We know how to make it not fade in the sunlight. But I doubt very strongly someone saying, oh, if we could add a little carcinogenicity, that would be cool, right? No, people don't want these things. So why are we doing it? So maybe instead of how we make molecules, we should first talk about how do we make chemists, right? I'm not a historian. Can't talk about the history of chemists, but for some strange reason, I became a chemist. Maybe there's something in that story. Okay, so I am, if you recognize the absence of my accent, I am from a city south of Boston called Quincy, Massachusetts, the home of not one, but two presidents of the United States. And in my opinion, one of the greatest chemists who ever lived, R.B. Woodward, is from my high school in Quincy. Got the Nobel Prize in '65 for the synthesis of vitamin B12. Had he lived longer, he certainly would have gotten 1, 2, maybe even 3 other Nobel Prizes. But I didn't grow up destined to be a chemist. I wasn't some child dreaming about pouring beakers and flasks and things like that. I was a musician, all right? I'd had no real fundamental exposure to science as a child. It wasn't something that was in my DNA, so to speak. I played in a band. But the name of the band that I played in was, wait for it, The Elements. Had nothing to do with carbon, hydrogen, nitrogen, oxygen. It was a Rubik's Cube, a glass ball. Hey, it was the late 70s. You know, those were our elements, okay? We kind of sounded like the band The Cars, but with better lyrics, okay? And we were pretty successful. We were playing 3 nights a week at the worst dives in Boston. We were in a recording studio and things were happening. and disaster happened. And my close friend and the drummer of the band ending up getting a form of leukemia and very quickly passed away. And as a 17-year-old child, this was an existential crisis for me. My whole life was about music, right? So I was going to the University of Massachusetts, Boston, as a undeclared but intended to be a music major. But I had to take a core set of courses. And so I kind of like biology, mitosis, meiosis, genetics, that's kind of cool. I kind of like physics, subatomic particles, astronomy, that's kind of cool. I couldn't decide. Should I take physics? Should I take biology? Should I take physics? Should I take biology? Then the moment of inspiration added up, divided by 2, I said, I'll take chemistry, because I couldn't pick between biology and physics. So here I am as a student in the teaching lab, taking chemistry, having this existential crisis about what I'm going to do in the world, and this professor comes in, Professor Jean-Pierre Anselme. And he looks at me, music major, walks on by, and looks at the student next to me and says, would you like to do research? I kind of heard and I said, can I come? And I followed him into the research lab. And when I got into the research lab, everything changed for me. All my life, there were 2 types of people. There were artists and there were scientists. And because I was marginally acceptable at music, I must be an artist. But when I got into the research lab, and I found out that chemistry was more than PV equals nRT, that people designed things, people created things. I imagine putting some helmet on my head and composing a piece of music and creating some neurological blips on a screen, and then designing a molecule. And I said, I bet you the same blips happen. That bringing something into the world that didn't exist before, that's not art. That's not science. That's something far more human. And so I fell in love with chemistry. Next thing you know, I'm spending 40, 50, 60 hours a week. And by the time I'm 19, I published 5 papers in journals and realized I'm pretty good at this thing, chemistry. In fact, in 1983, at 20 years old, I spoke at the first ACS national meeting. Now, I intentionally made this sepia colored because I feel very old with this thing here. But I realized this is where I belong. And it was such an amazing feeling to have surrounded by such diversity, but with a common focus. So next thing you know, I find myself at Princeton University working with Professor E.C. Taylor. I lose my friend to cancer. I'm going to do cancer research. Why not? And I am insanely productive and publish a ton of papers as a graduate student. And several of these papers ended up becoming the molecule Alimta, the drug sold by the Eli Lilly company, a very successful anti-cancer drug. Now, interestingly enough, when I'm working in the lab, the former Princeton employee who was working at Lilly was involved in that tech transfer, just so happens to be our new president-elect, and small world, isn't it? And so if you come to the Princeton campus, you see this amazing chemistry building built entirely on the proceeds of this one molecule. Okay, so I'm in my lab. I'm trying to decide what I'm going to do next. And one day, out of the blue, a senior corporate officer from the Polaroid Corporation, Dr. Lloyd Taylor, comes and visits me. He brings me out to lunch and on the spot offers me a job heading an exploratory research group at Polaroid. I go, I'm a medicinal chemist. I'm going into academia. He told me how much he was going to pay me. I said, when do I start? And all of a sudden, I'm an industrial chemist. How did that happen? All right. And so Polaroid at this point was one of the coolest places to be as a chemist. Bell Labs had kind of gone away, and so the creativity, the imagination, Edwin Land, one of the most greatest U.S. American inventors, what an opportunity. But what would a medicinal chemist do at a place like Polaroid? As a medicinal chemist, I'm used to working in cells, bags of water at room temperature. Now all of a sudden I'm manufacturing products at high temperatures and pressure. So I wish I had a lot more time. I would go into this. My passion is, I came up with this concept called non-covalent derivatization. Essentially what I said is, why is it that nature outperforms us humans? And, but not only in the elegance of the molecules, but everything in biology is manufactured at room temperature, ambient pressure, using water as a solvent. Why? And what my theory is that in nature, we chemists, we look at a molecule as if it was halfway between Jupiter and Saturn in the deuterated chloroform NMR tube. But in reality, molecules snuggle up with each other. They interact with each other, with the environment, with the solvent molecules. And I said, if we could, instead of derivatizing a molecule, methyl ethyl propyl butyl futyl, could we derivatize the non-covalent structure? And so started filing patents about how to look at the crystal structure and predict behavior, and making metallurgy, what I called organic metallurgy. I'm such a nerd. The license plate of my car is NCD, and so don't get me going about this. But I was so honored that I received the Perkin Medal for the creation of the field of non-covalent derivatization. The pharmaceutical industry ended up creating all kinds of a regulatory structure of what they call as a subset of non-covalent derivatization as co-crystals, which I had the honor of participating as a science advisor on that. So I realized, using this framework, I was able to file almost 50 patents within 4 or 5 years. The non-covalent derivatization, acid amplification, biomimetic thymine photoresists, mechanochemical engineering, triazine photopolymer. We just really had a blast inventing, but I didn't read a paper and say, how can I use it? I invented fundamental chemistry as a way to solve a problem. So this concept of fundamental and applied always confuses me. I don't think chemistry is ever fundamental or applied. The individual doing it has a bias of such. But chemistry doesn't know what it's doing. And so I really loved inventing a new process to solve a problem, and was very fortunate to get a lot of products on market. But what is it you need to do when you manufacture in the United States? You can't just do it. You got to get EPA approval. The Toxic Substance Control Act, TSCA. And so back then, this was before the internet, okay, so we had to do, banker's boxes full of copies of low volume exemptions, pre-manufacturing notifications. And to aid in the process, Polaroid sent me to Washington, D.C., that's probably one of the first times in my life I was on an airplane, really scared and nervous, holding a briefcase of overhead transparencies. And I had to go meet this scary guy named Paul Anastas. Wait a minute. I know this guy. Remember the person that I followed into the research lab when I was a music major? It was him. Okay, we graduated together. We were lab mates together. In fact, we published a paper in JChemEd, and it came out in 1985. We actually did the chemistry in 83. You are very old, my friend. Okay, and in fact, I played in a kind of funk band with his older brother Nick, kind of like Tower of Power, but without as good of lyrics. And so there's me, there's my older brother, and the guy playing the guitar. If you've ever been to Las Vegas, see the big billboards. The guy that plays Rod Stewart in Legends of Rock, that's the guitar player, okay? Has nothing to do with this talk. This talk's kind of cool to show that. Anyways, so here I am. Polaroid has been manufacturing stuff with all these solvents, all these energies, all these hazardous reagents. I've come up with something that works better, costs better, is aqueous, has low energy, is non-hazardous. It just so happens that Paul at the EPA is creating this thing called green chemistry. And this is an industrial process that is going into manufacturing that articulates it. So here I am, I'm 27 years old, I'm interacting with people in Washington. I have now a bunch of patents, a bunch of papers, all the stuff. My head is this big, I am the greatest scientist who ever lived. And disaster happens. And I lose my 2-year-old son to a birth defect. My son John is born with a disease called biliary atresia, where his liver is detached to his intestines and he couldn't metabolize water-insoluble nutrients. He got a surgery at birth, and by 2 years old, we lost him. Lying in bed the night of my son's funeral, I'm asking myself, did something I touch in the lab cause this? Did something, heaven forbid, that I got an award for cause this? The answer to the question, well, really frustrating. What really drove me crazy is I couldn't answer the question. And I got thinking, every year in the world, we graduate about 450,000 undergraduates in chemistry. We graduate about 125,000 master's degrees in chemistry, about 30,000 doctoral degrees in chemistry. In 2004, more women started becoming chemists than men as undergraduates. What could be more important to the field of chemistry than some kind of understanding of the molecular shape and structure and its potential for doing harm for human health and the environment? And yet what I realized, not one chemistry program on the planet required chemists to learn this stuff. So why do we have these things? It's not an epic battle of good and evil between industry and environmentalism. For some strange reason, the field of chemistry has evolved to not see this as part of what we teach students. And if that's not what we do, who did we give it to? All right, and so we needed not a social movement, not a politic, but a science. And so Paul and I, we wrote this book, Green Chemistry Theory and Practice, and just so proud of it. We were very frightened to publish this book when we first did it. We were really a little bit scared about doing it, but felt it had to be done. And we wrote the book, and still today, 30 years later, people come up, oh, well, what is green chemistry? I don't really understand. Now, well, 30 years ago, there's a book and there's a chapter called What is Green Chemistry? All right? And in that chapter, there's a definition. Green chemistry is the design of chemical products and processes that reduce and eliminate the use or generation of hazardous substances. Okay? And so I've just been so honored, amazed. This book has been translated into a bunch of different languages. I've been to, at last count, 93 countries, meeting kings and queens and presidents and prime ministers. But I'm just a name on a book. It's the amazing community, the thousands of people worldwide, many of them in this room right now, that are making this the movement that it is. And it is breathtaking. But all this advance, all these people, and they are amazing people, let us never forget these things don't happen spontaneously. They don't happen because it's the right thing to do. It takes vision. It takes leadership. And we wouldn't be here talking about green chemistry were it not for Paul and Astis. Period. Right? And so we wanted to craft these principles. Now, this isn't John and Paul putting fingers to forehead saying, thou shalt do. Green chemistry was already happening when this book came out. There were already Gordon conferences. The ACS was already having programming. There were books being written with people's research. And so we reflected upon what is it that a chemist can do to address issues in human health. But you'll notice climate change isn't mentioned. Social equity isn't mentioned. Environmental justice isn't mentioned. Plastics in the environment, because this isn't about the issues and the targets. It's the mechanistic chemistry that is necessary to address them. We didn't want to, every time someone discovered a new problem, have to write a new principle. This is a comprehensive way. We're talking about activation energy. We're talking about nucleophilicity. We're talking about catalysis. This is fundamental mechanistic chemistry and how that mechanistic chemistry is applied to designing products with improved sustainability and human health implications. I was so passionate about this. I loved working at Polaroid, and Polaroid had its bad days, and it looks like I was clairvoyant leaving beforehand, but actually I did, and I left at the height. I loved Polaroid, but I wanted to go into academia and really address this from an academic perspective. So I went to the University of Massachusetts, was director of biochemistry, full tenured professor of chemistry, full tenured professor of plastics engineering, and we started the world's first PhD program in green chemistry in 2001. Over the next 10 or 12 years, about 150 students at various levels went through this program. The average time it took one of these students to get a job, 2 days. The longest any student from this program spent looking for a job was 2 weeks because she turned down the first 5 job offers. I've been out of academia for 15 years. I'm still getting calls from companies. John, you got anyone coming? Because it's everything in a regular chemistry program, but it added to the regular chemistry a course on mechanistic toxicology, a course on environmental mechanism, a course on law and policy, everything that gets in the way of things making it to the real world. But here's the thing. If tomorrow morning everyone woke up and said, that's it, we're doing this, every individual, every retailer, every manufacturer, every brand, we're in trouble. By my estimate, maybe 10, 12% of the technologies today are truly sustainable. 90% haven't been invented yet. It's not that companies hoard better technologies. We, the chemistry community, haven't finished the job. There's a handful of things emerging, but the vast majority still need to be invented. And so the biggest barrier to sustainability is not banning products, is not passing laws, is not having social movement. If we chemists haven't invented it, we can't do it. I loved being in academia, okay? I really loved it. In fact, I was honored to receive the Presidential Award for Excellence in Science, Mathematics, Engineering Mentoring in 2004. Spent a half an hour in the Oval Office with this individual. Get a couple glasses of wine in me, I'll tell you more about that experience. But I left academia. I thought, what intelligent person would leave 2 full tenured professorships? But here's what happened. Because I'm an amusing individual, I guess, every time there's a sustainability thing happens in the world, some reporter, some journalist wants a quote from me. So I'm driving in my car and the phone rings, and it's a journalist. Canada just banned Nalgene plastic bottles, and they wanted to know what I thought. So being a dutiful citizen, I pulled over the side of the road, and I'm talking on the phone. I'm in the parking lot of a grocery store. And as I'm talking to him, a pregnant woman comes out of the grocery store. She's stumbling with her bags and her keys, and she puts her cash register, and some neuron in my head goes pop, and I go, you know what drives me crazy? Yes, bisphenol A is a critical issue. Yes, in plastics, this is really bad, but there are femtogram quantities of bisphenol A in plastic bottles. In a cash register receipt, there is milligram quantities of unpolymerized free bisphenol A. Holding onto a thermal cash register receipt for 20 seconds, you'll get more body burden than a lifetime of drinking out a plastic bottle. This, John, calm down. This is a story about plastics. But somewhere they mention John Warner reveals bisphenol A in cash register. I didn't reveal anything. It's National Cash Register's patent. It's just crazy. Next thing you know, hundreds of websites. John Warner reveals. I'm a guest on Tom Ashbrook, on Point. John Warner reveals. In this high impact factor technical journal, on the same page as a cat pushing a shopping carriage, John Warner reveals bisphenol, and I'm looking at this cat. I'm saying, something has gone tragically wrong in my life. I've spent all my time inventing technologies that are better for human health and environment. Nobody cares. And the one time, kind of by accident, that I talk about a problem, and I'm all over the place. I don't want to do that. I want to focus on solutions. Yes, it sells. Yes, people like it. But it's not what I want to do. And so my wife, Dr. Amy Cannon, and I, we were both professors at UMass. We made the decision, very difficult personal decision, to leave academia. And our shared visions, we envision a world where the chemical building blocks of products used every day are healthy and safe for humans and the environment. Amy started Beyond Benign, fostering a green chemistry community. And I started what was first called the Warner Babcock Institute to do research. And then we rebranded it over COVID to Technology Greenhouse. All right, and so I went from academia to being an entrepreneur, but not entirely. All right, so I still have academic positions at Monash, at Technical University of Berlin, Chulalongkorn in Thailand, Samaya in India, University of Birmingham in the UK, and RIT here in the US. So I still teach classes and advise students and things like that. But my main focus is I invent stuff with a wonderful team. But here's the thing again. I go to conferences all the time on sustainability, and still now, in 2026, most of the time, people are talking about why. They're showing pictures of disasters in the environment, horrible statistics in human health, and that's important. And then a lot of people talk about what we should do. Oh, we should do the UN SDGs, we should run LCAs, we should do circular economy. That's important. The urgency is important. The metrics are important, but the why and the what describe and measure the problem, but don't solve the problem. If we're going to solve the problem, we need to work on the how. And that how is uniquely a chemistry problem that is codified in the field of green chemistry. We are necessary, the American Chemical Society, the chemistry community, if we want to break this logjam and move on to a future that is sustainable and healthy for humans. It's not going to happen out of hopes and dreams. It's going to happen in beakers and flasks. All right? We need to reinvent how we invent. So being at this for a long time, I've kind of come up with this image of invention. And the way that I look at it, there's this land, and it's called the land of infinite molecules and materials. And far, far away, shrouded in clouds and mystery, is the land of infinite products. And over the last century, people in the land of molecules, they make something, and they say, hey, industry, do you like it? But it's too far. They can't reach it. And then the people in industry are looking for new materials, but it's too far and too blurry. And what I've realized over my last several decades is if you blow away the mist, there are 3 islands. I call them the islands of innovation. And it's all about, although there are infinite molecules and infinite products, the very finite number of mechanisms and properties. All right? So a product can be defined by a material property, what I define as a quantifiable consequence of mechanisms that directly relate to the performance and characteristic of a product. You don't have to be a scientist. You ask them, what do you want it to be? I want it to be blue. I want it to be stretchy. It just kind of describes what you want that product to do. That's not a molecule. But the next island over, which is easily accessible, is the island of materials, mechanisms. These are intermolecular processes between more than one molecule, or an intramolecular process over a nanometer in a polymer. This is stuff like crystallinity, chain mobility, Young's modulus, Hansen parameters. Still not quite a molecule. But the next island over is the island of molecular mechanisms. Those are intramolecular processes within a single molecule or within a polymer under a nanometer. That's stuff like bond rotation, van der Waals surface area, molecular topography, aromatization potential. Now we can look at a molecule and say, what does this molecule do? Now, what those mechanisms, what material mechanisms do they create? Now, what properties do they do? Oh, here's some products we could make. Or if we have a product, we go, here's an unmet need. We can go back and forth. So the mechanisms are the key to inventing solutions. However, if you want to do sustainability, you put it on the list. But if nowhere in your education did you ever talk about the mechanisms of those problems, how in the world are you going to invent them? So I could use this to invent the next Apple product. Okay, or I could recognize with a deep sense of humility that we've been doing chemistry for what, a couple hundred years. Nature has been doing chemistry for 3.8 billion years. We can look, instead of making an Apple product, look at an Apple product and ask, how did nature evolve the water barrier, the oxygen barrier, the viscosity, the nutrient transport? And if we with humility can learn, now we're on the pathway of making a truly sustainable economy. So technology greenhouse, people, whoa, what is that? Do you grow plants? You know, so technology greenhouses, 2 labs north of Boston, and got a really tiny group of people. For the last 20 years, never had more than 20 scientists working in the lab, never was blessed with an amazing budget. So really struggling year to year to make ends meet. But this tiny group of people using green chemistry and the islands of innovation were filed almost 380 patents in the last 12, 15 years, okay? I never name companies that I work with, all right? I've worked with over 120 companies inventing products. These companies had public press releases, oh, we worked with John Warner, and so I can say these things because they're in public. And what we do is we then create our own companies. So we have a pharmaceutical company, a cosmetic company, a construction company, a photovoltaic company, a consulting company, a biopolymers company, a water harvesting company, a flow reactor company, a pharmaceutical services company. And what I want to do is kind of give you a sense, what does some of these look like? What is green chemistry in the world of beakers and flasks? What does a chemist do? Okay, the first one is there's this molecule called copper ATSM. This stuff is brick dust, okay? It is insoluble in everything. If you dissolve it in DMSO with some surfactants and give it to laboratory animals, it's got really amazing neurological properties. But you could never do that with humans. So using non-covalent derivatization, we were able to customize the oral bioavailability and get it across the blood-brain barrier. We manufactured it using mechanochemistry, and it has sailed through phase 1, phase 2, phase 3 clinical trials, and is one of the most promising opportunities for ALS. Could not possibly have done this without the principles of green chemistry in the islands of innovation. Another example, one day, I don't know why I do this, never ask, I was contemplating insect sclerotization. It's the process in which when a bug gets bigger, it sheds its exoskeleton, and over the course of a couple hours, it turns hard and black. I'm going, there's a process in nature that goes from colorless to colored. People color their hair with some pretty nasty stuff. So I looked at it and I said, it's a tyrosinase oxidative cascade. I don't want to grind up dead bugs. I thought that was nasty. And so instead I found these velvet beans that have the same chemistry and invented an iron manganese couple, and essentially bought some gray hair, put it in, and oh my goodness, it worked. permanent, doesn't wash out, doesn't fade, but even more interestingly, it doesn't paint the hair. It restores the hair to its original color. Okay? So some people way back there, so it may be hard, but if you look really close, I'm starting to go a little gray, okay? If I why do people laugh at that? I don't know. I don't have any mirrors, okay? So if I put this in my head, it goes back to exactly the color my hair was 30 years ago. My friend who has black hair, it goes black. My friend with brown hair, it goes brown. This is all food-grade materials that you put in your hair, you rinse it out. You go, in the same way you have a fingerprint, you have a hair print. So one day, I'm doing experiments on my own head here, okay? And I go to a conference on semiconductors. It's a board meeting because one of the companies I'm working with, so I'm at a board meeting working, and everyone's looking at me kind of funny. And I go, oh, and I explained what I was doing. And they go, oh my God, that's amazing. One of the people at the board, they go out, they raise a ton of money, and they start a company called Hairprint. And for the last 12 years, direct to consumer, myhairprint.com, act quick, they'll throw in a set of knives. You can get this box that colors your hair, non-toxic, environmentally benign. Could not possibly have done this without the principles of green chemistry in the islands of innovation. Another example, if you take all the asphalt in the United States and smush it together, it's about the size of Wisconsin. All right? And the sun and the air oxidize the surface of the asphalt, making it brittle and hard. So we repave 10% of all asphalt roads annually. All right? But because it's brittle and hard, we just take the stuff, put it in a landfill, maybe use a little bit of it, and buy new petroleum and new aggregate and put it down. And it kind of drove me crazy. I go, why? Interesting enough, remember, I worked at Polaroid. Do you know that in the 1800s, the first photograph that humans made was from asphalt? That, no kidding, it oxidizes in the air. We used to make photographs out of this stuff. So having that idea, I said, I bet you I could invent a catalyst that reverses the oxidative process. So in 2013, if I'm willing to put stuff in my hair, we dug up my driveway. We went to the asphalt mill. I climbed up a ladder, put the catalyst in. They came back. They were laughing at me. John, you're an idiot. This is not going to work. It worked. It outperforms industry standard with no new inputs. And so we started a company called Collaborative Aggregates. I wanted to call it Entropy Mix. I thought that was a cool name. And someone said, oh, that's a stupid name. So I go, how about Delta S? Don't tell them what I did there, okay? And so Delta S is the catalyst that goes into the asphalt, and Delta Mist is an aqueous emulsion that preserves it. From an idea in my head to first sales, 18 months, okay? This could not have been done without the principles of green chemistry and the islands of innovation, all right? You know the glasses that you go outside and they turn dark and they go inside and they turn clear? Well, I played with the molecules and made it so it goes hydrophilic to hydrophobic. If you make a super hydrophilic polymer, great, it sucks up water. But if you want that water out, that hydrophilicity works against you. But taking and putting a passive switch in it, again, this is a cartoon, but imagine an umbrella and that the sun shines, water absorbs on the underside of the umbrella, sun goes down, and it rains pure water, and it cycles. And so we started a company called Mist Miner, and our first product, hopefully next year, is an indoor dehumidifier that instead of compressed cycling, it actually has a light flashing, and it's 1/100th the energy use of a typical dehumidifier. Could not have done this without the principles of green chemistry and the island's innovation. Here's one of the ones that I'm really excited about. I created a wireless UV LED, all right? So it has an on state and an off state, and then I coated it with a catalyst, all right? And I fill a flow reactor with it, and I put it around an induction coil around it so it can turn on and off different regions of the flow. And doing this and controlling the catalyst, the photocatalyst. Think of all the papers that have been published on photosynthesis and photocatalysis, but none of them really make it to the large-scale manufacturing. Now all of a sudden, we can do photocatalytical synthesis, we can do degradation, and we can do chromatography. Instead of having the mobile phase change, you have the stationary stage change polarity. Really kind of fun. And then the last example is combining Kibotics, which is an AI machine learning company, and my science of non-covalent derivatization. We created an AI co-former company where we take solid state chemistry, work in pharma to improve the performance, get new intellectual property. So it's kind of a balance between making a new covalent derivative and a formulation. And that, but a little bit of a secret out, we now have a GLP NCD that we designed that is 10x more orally bioavailable than Novo Nordisk's one that's on the market. So it's pretty exciting technology. All right, so I talked about why, I talked about what, I talked about how. Left out the most important. Who? All right. We've got the American Chemical Society Green Chemistry Institute with Adelina Rojkova and her amazing team doing amazing things. Okay, we have Martin Rommel in Germany on the Chemical Innovation Factory. The things that happen to me in the world, I'm just so flattered, so amazing. They named a building in Berlin, the John Warner Center for Startups in Green Chemistry. Next Friday, they're having a roof-topping ceremony. This organization, led by Martin, has raised tons of money in the European Union to help startups. Sonja Jost, another amazing individual in Germany, is working with the Association of Industrial Green Chemistry to create a catalyst center there. And then my personal hero, and I'll try not to lose it in front of everybody right now, but Dr. Amy Cannon in Beyond Benign. And her amazing team runs the Green Chemistry Commitment. And this is changing the world more than anything, in my opinion. This last week, we celebrated the 300th college university in the world that has committed to bringing green chemistry into the required curriculum. I can go talk to a CEO of a company and have influence. I can go to a politician and have influence. Try to change curriculum at a university, all right? And Amy and her team are doing it. It's amazing. And so I just want to finish with some quick last thoughts. We live in an insanely polarized world, okay? Should we recycle or should we have biodegradation? Let's fight over it. Should we have industry funding? Should we have academia doing it? Let's fight over it. Should we have public funding? Should we have private funding? Let's fight over it. Is the left right? Is the right right? Let's fight over it. Toxics, climate, paper, plastic. We're fighting over everything. And I think we chemists have a unique opportunity to weigh in a very different level. Because think about it. When we chemists talk about matter, is it a particle or is it a wave? We're comfortable with it being both. Is the left structure of benzene the correct one or the right? We're comfortable with it being both. With taumerization, is it diketone? Is it the diketone? Is the hydrogen bond going to the left? Is it going to the right? We're comfortable with it being both. When we fill electrons in an orbital, that last one, do we have to pick a winner? We're comfortable with it being everywhere. And finally, in energy, is there team enthalpy and team entropy? We're okay. Maybe our whole science of understanding different perspectives simultaneously superimposed on themselves is something that we need to offer society. Something magical, and we take it for granted. But we need humility, humility, humility. We say, oh, chemistry is the science. We are the center of the universe. Chemistry creates biology. Biology creates neuroscience. Neuroscience creates philosophy. Philosophy creates mathematics. Mathematics creates physics. Physics creates chemistry. There is no center. This is a continuum. In fact, astronomy, biochemistry, music, architecture, accounting, engineering, we're all in this continuum. Chemistry is everything, but so isn't everything else. And so if we're going to have impact, we got to recognize that we're part of this continuum, and that's even better than being the most important, right? So thank you so very much for giving me the honor of sharing my thoughts with you today. And thank you, the American Chemical Society, for everything you're doing. And happy 150th. Thank you.
You're supposed to say I'm coming on stage, but great
you.
job, great job.
Thank you.
Thank you, Dr. John Warner. I already see one person at the mic. I think Dr. Warner would be happy to take a few questions. I'll direct that if you do want to have a question, please go to the mics on the left and the right, and I will take turns for maybe a couple minutes while there's still time. So first on the house right, please.
Okay, great talk. When you were talking about the question of BPA and being toxic in water in bottles, and then you said, well, there's more toxicity in BPA in the receipts. It kind of reminded me of a story, and I would like to know what you think and what in the political and scientific solutions, what you think. So back in 1997, my parents were working at Brookhaven National Lab, and there was a very small leak in the nuclear reactor. It seems like you know the story?
Mm-hmm.
So essentially, there was radioactive water. I don't know what the concentration of how much tritium water was leaked, but it was only 30 liters per day in a tank that was 260 cubic meters. So it wasn't a very big environmental leak. And if you're on Long Island, you do more environmental damage by pouring your car oil into the groundwater, which will reach the aquifer. But it was a very big political issue on the local, state, and federal level, and people were vilifying Brookhaven National Lab, and we had congressmen, we had Congressman Forbes, we had Senator D'Amato.
My apologies. Would you please get to the question?
Okay, so I already asked the question, but I'm giving the story.
All right.
Yes, but it's been 2 minutes.
Okay, so I thank you. Very important. What's most important about green chemistry is that chemists have cared about human health and the environment since the beginning of time. This isn't the birth of ethics. When I was a music major, I actually asked my professor, if I become a chemist, will I put myself and my future family at risk? And his answer was, if you're asking that question, maybe you shouldn't be a chemist. And so I didn't. Now, how we dealt with it is we've always dealt with exposure. And the problem with mitigating exposure are things go wrong, and they have great expense to the organizations doing it. The revolution that is green chemistry is shift the focus to the intrinsic hazard. When you make it intrinsically non-hazardous, now you don't have to focus on the manipulations of exposure because it's just intrinsically non-hazardous. That's how we get to a safe future.
With my apologies, we don't have a lot of time, so we're going to take only 2 more questions, one on the house right and one on the house left. I'll take Lily DeAngelo's question first.
Thank you. Thank you, Dr. Warner, and congratulations for being a Kavli lecturer.
Thank you.
I really enjoy your lecture and you're a great storyteller. So I actually have 2 questions, very short one. One is today, scientists and chemists do lost trust of the public. So the question is, how do we as a chemist be a better communicator to communicate the chemistry, the benefit of chemistry and what we do to benefit society? And two is, how do you become such a great communicator?
A lot of people that'll disagree with that last part, but so I do think we need to be much better at how we communicate to the general public. Tomorrow from 2 to 5, there is going to be a screening of the Netflix documentary Plastics Detox. And I'm in it a very small part, less than 15 minutes, but I've gotten some criticism about being in something like that. And I feel that we chemists have to be part of this. Yes, is it sensational? Is it loose on facts? Maybe, probably yes. But is it an important issue? And if we chemists just criticize the facts, the general public sees us as somehow supporting the problem. And so we need to understand how we communicate to the general public better. And it's scary, it's hard. It is so much easier to talk to a group of people and say, oh, I've been working on this SN2 reaction and the nucleophilicity of the highest occupied molecular orbital. And everyone just nods their head. All right, try to tell a 5th grader that. Okay, we need to be better at talking to non-scientists, and we deserve the mistrust because we haven't done a good job.
Thank you. One last question. Let's try to keep it tight.
I'll keep it real tight. So, John, often when we talk to people about trying to use green chemistry and sustainable methods in production in chemical engineering, they refer to what they call the green burden. They're saying we'd love to be sustainable, but we can't afford to have the added cost.
Yeah.
But in your book, you talk about the importance that green chemistry isn't green chemistry unless it's also economically viable. Could you comment on that?
Yeah. So I think that the ability of companies to fail is extraordinary and quite common. And so, unfortunately, in 1990, about 12% of R&D made its way to commercial product. 2026, we're below 2%. We as a society have lost our ability to get products to market. And there's a whole bunch of different reasons why that is so. All right? And the mistake people make is when they list the difficulty in getting green chemistry technologies to market, they end up listing all the problems that any technology would have getting to market. All right, and so what they're missing the point is green chemistry is not a barrier. Green chemistry is a tailwind to help address those barriers. But the magical thing is if one approaches a problem and says, this is a barrier, whether it is or isn't, it is now for them. All right, I can't help people's misperception. But that's why there's not so many successful companies that grow into big companies. Most endeavors fail because people have strengths and weaknesses. Their ability to understand the reality of the situation is probably their biggest barrier.
This has been amazing, Dr. Warner. John, thank you for sharing everything. I want to just ask you one last question. I mean, I really wanted to ask you about how many green principles we need and how many more we need and what A is going to do. I'm going to let you answer that with those on the floor, but they all want to know one thing. What is your favorite ice cream?
My favorite?
What is your favorite ice cream?
Oh, it depends on my mood. Sometimes pistachio.
That's green.
Yes, it is. And then sometimes I like coffee.
Coffee.
Yeah.
Great.
Okay.
Well, now you know what his science is and what ice cream you should have tonight to celebrate it. Thank you all.
Thank you.